and welcome to session 2 of Unit 3. This session will introduce you to nuclear binding energy. By the end of this session, you would be able to do simple calculations involving nuclear binding energy. Let us begin by looking at binding energy. The binding energy is the energy that would be required to disassemble the nucleus of an atom into its component parts. These component parts are the protons and neutrons, which we collectively call nucleon. The binding energy of nuclei is due to the attractive force that holds those nucleons together, and it is usually a positive number, since most nuclei will require the expenditure of energy to separate them into individual protons and neutrons. It is always possible to calculate the binding energy of a nucleus if you have the mass and the mass of the nucleus and the mass of the composition of the nucleus. For example, if you have helium atom and we have to calculate the binding energy, the energy that is required to disassemble the nucleus, then we need to know the mass of the atoms of the nucleus, the subatomic particles of the nucleus. We need to know the mass of proton, and mass of proton is given by 1.00728. And since there are 2 protons in the helium atom, we multiply that mass by 2. We need to know the mass of neutrons, which are also given here, 1.00867. And since there are 2 neutrons, the neutrons are given by mass number minus proton number, which is 2. So 4 minus 2 will be 2. We multiply the neutron mass by 2. Having gotten these values, we'll put them together to get the mass of the sum of the mass of proton and neutrons. And when we do that, we are getting something like 4.03190 atomic mass units. And the actual mass of the helium atom is 4.0026. So we subtract the actual mass from the sum of the masses of proton and neutrons, and we will get the mass of the mass defect. That's the change in mass. So the change in mass, if we calculate by subtraction, we are going to get the 0.0293. Once we get this one, we can go ahead to use the Einstein equation to calculate the binding energy, where the binding energy is given by the mass times speed of light squared. So if we know the speed of light, which is approximately 3 times 10 to the power 8, we can substitute for the E to get the binding energy. If a system loses mass, it loses energy, and if the system gains mass, then in a way it's gaining energy. And it's good we note also that because the C is squared, the speed of light is squared, it shows that even a small mass loss can cause a large change in energy. So with a small mass, it's going to provide us a large change in energy. And that is why conservation of mass seems to hold in chemical and nuclear reactions. Let's look at this example, which is calculate the mass defect and binding energy for uranium-235. One uranium-235 atom has a mass of 235.043924. Now, to calculate the mass defect, we use this equation over here, which has to make use of the atomic mass, which is A, atomic number Z, and then the mass of the atom. So in this case, we are multiplying the sum of the mass of proton and electron by the atomic number, which will add to the mass of the atom minus the proton number, and we multiply it by mass of neutron. The answer we finally subtract it from the mass of the atom. Uranium we know has the atomic mass of 92, mass number of 235, We know the mass of proton, mass of electron from our previous slides. And so when we substitute all these values into the equation, we'll end up finding the mass defect, that is change in mass, to be 1.91517 atomic mass unit. Now, to calculate the binding energy, then we need to convert the atomic mass to kilogram, and we know that every 1 amu is equivalent to 112 the mass of carbon-12, which is equivalent to 1.661 times 10 to the power 27 kilogram. So we have to multiply the change in mass by this factor, and after multiplying it by that factor, we will have to multiply the answer that we'll get by the speed of light squared, and that will lead us to an energy of 2.85 times 10 to the power negative 10 joule. This is a self-assessment question which I would want you to try your hands on.